So we have the great pleasure to welcome Ulrich Schneider from the University of Cambridge. We're working with the University of Cambridge within the Simons collaboration, but it's with Richard Friend from the very famous too. And so Ulrich will speak today about localization of ultracold atoms in optical quasicrystals, a subject that was slightly touched yesterday, but I think that will be a welcome talk about that. So you have about between 35 minutes at all, so 30 minutes plus 5 minutes questions, or okay.
Perfect. Okay, thank you very much. I come from a different background. This is all very much centered on optical lattices, so it's a slightly different set of tools, a slightly different set of conventions, and slightly different set of mental models and thoughts behind this. So therefore, I welcome questions also during the talk. Just raise your hand, and I hope I will see it. Otherwise, our chairman will hopefully interrupt me.
Yes, so I'm watching over so I will tell you if there is anyone raising his hand.
Perfect. Thank you very much. Good. So I can skip half of my normal introduction slide because you all know very well what Anderson localization is. And you also know that if we have the interacting system, we have many-body localization, or we can have many-body localization. That's, of course, a topic that has gotten a lot of interest in the last 10, 15 years. And my take on this is a particular angle. What is the particular point about having a many-body localized insulator compared to, say, a mod insulator or a band insulator or any other insulator? And from my point of view, the most important point, the unique point about MBL is that you get non-ergodic behavior. So you really get the behavior where you don't have thermalization, you don't have standard statistical mechanics, you have the potential for novel long-time dynamics, and in particular, you have for long times a memory of the initial state. And that's kind of like the main idea that we use. So we will not very much look at localization in terms of particles are pinned to a certain point and can't move. We more have the thought in mind of saying the particles will remember their initial state. So the typical way how this was probed in optical lattices in our group, or in Immanuel Bloch's group where I was before I came to Cambridge, in the last couple of years was really that we said, okay, let's start with a slightly disordered lattice. So you can see the lattice potential is a bit disordered here. And we start with a state that's very far from an eigenstate because we only put particles on the even sides of the lattice and the odd sides are empty. And then we just said, okay, let's time evolve, let the system evolve freely. And then what happens after long times? Well, if the dynamics is ergodic, then the time evolution will certainly destroy this initial charge density wave because it's not an eigenstate of the Hamiltonian. There's nothing distinguishing globally between even and odd sides. So therefore, all time evolution should wash out this information about the initial state. You turn this argument around. You say, if I have a persistent charge density wave for long times, then it's pretty clear that I have a non-ergodic dynamics, a non-ergodic behavior, and that means I have localization. And we can monitor this very simply by looking at the so-called imbalance. So we just ask, what is the difference in atom numbers between the even and the odd sides? We have a high imbalance in the initial state, and then we can just time evolve, and then we ask, how much imbalance do we have left? And this is the main graph from our first paper, which is by now 5 years old on this. And you can see that U is the strength of the interaction, so we can have repulsive interactions and attractive interactions. And delta in this case is the strength of the disorder. I will specify this more on the next slide. And you can see that up here we are always dark red, which basically means even for strong repulsive, strong attractive interactions, we always have a localized state. So it's a direct observation of many-body localization on the experimentally accessible timescales. So the limit in all of those lattice experiments is not the system size. These are like chains of chain length 100 or so. The limit is really the accessible timescales because we can't really say what happens at very long times because as any cold atom experiment over very long times, in our case of several seconds, there will be a problem because other processes take over. So we then studied like many aspects of this in more detail, and because this talk is not about many-body localization, I will skip all of them. But I will now say what is the kind of potential that we used for this. What we used is a so-called Opulent-Tree model, which basically said that we superimpose two incommensurable lattices. So we started with a rather deep lattice, say 7 recoil, so we are in the tight binding regime. And then we said we take a second weak lattice to slightly perturb the energies of the first lattice. And in this case, 532 and 738 nanometers, the wavelengths, means that this is close enough to an incommensurable situation. So this potential that we now get, this modulation that we get of the on-site energies in our tight binding chain, is not periodic. It has the structure that has a certain, if you want, periodicity to it, but this periodicity is not commensurate with 1, not commensurate with the lattice structure, and therefore if you write down the Hamiltonian, you end up with the O'Brien tree model, where you basically have a modulation here that's sine 2 pi beta I, and beta is an irrational number, so it makes sure that the system is not just a superset that repeats itself, but it's really an incommensurate situation. And as we already heard, there's important differences between this and the real Anderson case with a purely random potential. The main one is that, of course, in 1D Anderson, localization happens for any positive strength of the disorder strength, while in this case, we have a localization transition which is pinned precisely to the point where delta over J is 2. And that's due to a symmetry in this model, the so-called O'Brien duality. You can show that basically if you exchange J and delta, it's basically a Fourier transform that maps the one term onto the other term, and the self-dual point is exactly at delta over J2. So that's the point around which everything must be, in a sense, symmetric. If I plot for single particles the localization length that I get from this, here in orange, there is the localization length of the Anderson case. Here in blue is the localization length of the quasi-periodic situation, which of course diverges at this delta over J2. But if I think about the regime of strong disorder that was so far typically looked at in many-body localization, you would say that there actually the localized phases should be very similar deep in the localized regime, as the system cannot really explore these long-range correlations that you have in the quasi-periodic potential if your localization length is very short and each atom can only like see a few lattice sites. If you want to analyze the system now, not on the many-body, but on the single particle level, you can of course go much further, and you can ask, how does this localization transition in the O'Brien tree model really happen? What are like critical exponents? Is there a typical critical dynamics? What can we say about this? And we asked many colleagues about that, and we didn't get the answers we wanted, so we had to start doing a little bit of theory ourselves. So a very useful tool for looking at this is to realize that you can take any irrational number beta and write it as a string of integers n1, n2, n3 using the so-called continued fraction expansion. So you're basically saying I take my beta and I approximate in the first step as 1 over n1, where n1 is an integer. If beta was irrational, this is of course not going to be correct. So you have a small correction plus beta 1. And this small correction in the next step, you do the same approximation. You approximate beta 1 by 1 over n2. And you again get a little residual beta 2 and so on. So you can map any irrational number onto this string of integers. And this turns out, if you think about renormalization group, if you think about physics in bigger and bigger systems, that it has a very intuitive explanation of what happens in the physics. What you see here in this diagram is a tight binding plot. So the lattice sites are the black dots here. And then the quasi-periodic modulation is this black sine wave here. And you can see that it's not exactly periodic. The period here is not just n1, it's n1 plus beta 1. And if you now would assume in the first situation that you would replace this with a wave that had periodicity n1, this is your first periodic modulation of the system, then you would get an extra term, which would then be the green line. It would again be a modulation which is not periodic, and that just takes care of the errors that you've done. Beta 1, 2 times beta 1, 3 times beta 1, and so on. And in the next step, you can approximate this one again with a longer length scale, a periodic potential of the length scale n1 times n2. And then again, you get a residual, and you can again develop this and so on. And you can basically make an approximate RG scheme based on this discrete RG that was first suggested by Suslov in the 80s. And basically what you can see when you think about this physically is that these increasing n1s and i's, they give rise to a sequence of increasingly larger length scales. You have the length scale n1, n1 times n2, n1 times n2 times n3. So the system is governed by a whole hierarchy of length scales which get bigger and bigger and bigger, and they grow without bounds. If your beta would be periodic, the irrational number, then it would essentially stop at some point, and you would have a longest length scale, which would then typically be the size of your supercell over which the lattice repeats. But if it's irrational, then the sequence never stops, and you have a whole sequence of diverging length scales, which basically means when you think about this in terms of critical phenomena and so on, critical RG scales, you would expect that you never get a standard power law scaling regime, because whatever length scale you look at, you're never larger than all typical local length scales. And that's of course an artifact or a consequence of the point that these quasi-periodic potentials are long-range ordered, because there's no real randomness in them. So if you, for instance, try to look at the localization transition, here we look, for instance, at the decay of the superfluid stiffness as a function of approaching the phase transition. Then if we take a certain particular number, the silver mean 1 plus square root of 2, the continued fraction expansion is periodic, so it's period 2, 0, 2, 2, 2, 2, 2, 2, and so on. Then basically what you get is the blue line, which might look deceptively like a power law. If, on the other hand, you take something where you say only the first 10 coefficients are 2, and then you start going into period 6, then you will see that at some point here, close to the phase transition, this turns around and goes into a different slope. So minuscule changes in beta can totally change the behavior very close to this transition. I can also look at this with different periodicities, and I can see that for general beta, there is no typical universal regime. So these phase transitions are very interesting and very complex, and something that could be studied in a lot of detail, but of course it would require very large system sizes. So for us, this was more like a theoretical result, which is nonetheless very interesting, and it's a very good way of thinking about quasi-periodic systems, in thinking of systems that have longer and longer length scales built in. So you directly get like a structure of fractality in the system. Another interesting result we got from this is that we could do a scaling analysis, and we could see that there is, even though everything depends crucially on beta, there's a lot of universality, and you can actually get a perfect scaling collapse between different models at the same beta. So you can take this O'Brien tree model, you can also take a generalization where you also modulate J, and most interesting for us, you can also take a situation where both lattices are weak and both have the same strength. So it's not a weak tight lining lattice plus a small periodic modulation, it's now two weak lattices on equal footing, and they will also give rise to a localization transition, and it turns out that this localization transition has the same critical exponents than the one in the O'Brien tree model. So the critical parameters depend on beta, but they're universal between different models at the same beta. And from this on, you can go a long way into number theory and think about how this all depends on beta, but that's not what we're doing, what we want to do. I now want to first take a jump back to MBL and start to talk about many-body localization in 2D. And I will not say much. I will just say that it's not fully clear on the theoretical side whether 2D MBL actually exists and can actually be stable. The crux of the matter is that in every real random potential, if you take a string of random numbers, you will typically have a certain roughness, but you will also have local regions where locally all of the numbers are just by chance very similar. So you will have local bubbles, local enclosures that have a much lower disorder locally than on average. And the question is whether these rare ergodic enclosures in a big many-body localized system, whether they can actually, in an avalanche effect, eat up the whole system and localize and thermalize the whole system. And that's a question that is still being discussed. And of course, the problem that people run in here is that you can't solve this classically numerically. You need quantum simulators simply because an interacting 2D system is for big system sizes beyond what can be numerically simulated. So let's try to look at this first also in the non-interacting case. Let's try to look at the localization transition in the 2D O'Brien tree model. In the follow-up to our first work, we just looked at this, and we found that if you want to have the O'Brien tree model in 2 dimensions, also with a self-duality around lambda equals 2, you have to put the disorder along the diagonal. So you have n plus m as one term in the quasi-periodic modulation and n minus m as the other term, where n and m are like your x and y lattice directions. If you do this and you do the typical localization analysis, so you ask how does the participation ratio of the states as a function of the energy scale and change with the disorder. Here you see in the insert the 1D case, you see that everything is delocalized for lambda for delta less than 2j, and everything becomes localized above this delta equals 2j. And you see the same kind of symmetry in 2D, but you see the structure is much richer. You see in particular there's a funnel of states here which remain bluish, which means that they are delocalized even for rather strong disorder potentials. So we see a very interesting spectrum. We see kind of a funnel where we have an interspersed, localized, and extended states. If we are outside this funnel at higher or lower energies, then we have only localized states. So it's not a situation that we would have in Anderson in 3D, that we would have a sharp mobility edge. Because we're now in the lattice, of course, we have positive and negative energies the same. So it's symmetric around the middle, and it gives us a much richer structure with interspersed, localized, and pseudo-extended states. So let's take one of those states. Let's take one state that's delocalized, say somewhere up in here, and ask how does the state look? And if you then look, you see that this state has a very interesting structure. This is the density of that state on a logarithmic scale as a function of real space coordinates x and y. And you can basically see that it kind of like has some kind of fractal structure to it. And it's really mostly localized along a few dedicated special lines. And this is actually rather easy to understand. If you just think about, you have the sum of two cosines, n plus m plus cosine n minus m. And then we can, of course, rewrite this in the form of a cosine n times cosine m. And this means we can think of these lines along, say, the m direction as a 1D operant tree model, where the prefactor, the strength of the operant tree modulation, the strength of the disorder lambda n, now is proportional to cosine 2 pi beta n. And then, of course, there will be some numbers for which beta n is very close to a multiple of pi over 2, so that we end up with situations where this prefactor is very small. So we always end up with a few discrete lines, this line, this line, this line, that have a rather weak disorder in this direction, in the vertical direction. And this means, as we can also see directly, that we can discuss them as 1D operant tree models. And then if we are in the energy range where the 1D operant tree model is still delocalized, then indeed we also get like a quasi or pseudo-extended states, if you want, in this system. So we have rare regions also in this quasi-periodic potential, but they have a fractal structure to it. They're locally one-dimensional, which basically means there's no avalanches expected, because they're like spatially separated from the localized states, so they shouldn't hybridize. And that means that this system should really be a perfect system to look at MBL in 2 dimensions. The downside, of course, again, is that this is a tight binding model. So timescales are slow, timescales are large, dynamics is slow, and the question is, can we observe the system for long enough to really make statements about what happens for close to infinite times? And then there is, similar to 1D, a way out of this, which is the way to go to an optical quasicrystal, leave the tight binding limit, and see localization at much lower lattice depths and therefore faster timescales. So basically now, if you think back to my title slide, you can already guess what is happening now. And I will now introduce what do I mean with 2-dimensional quasicrystals. For this, I first go back to solid state physics 101, and we can talk about periodic crystal structures. We know that we have the crystallographic restriction theorem, which basically tells us that a periodic crystal can only have 1, 2, 3, 4, and 6-fold rotational symmetries. And the reasoning for this, you can see right away by just looking at the diagrams. If I have a 4-fold symmetry, that gives me the symmetry of the square. So it's what I expect for a cubic lattice. If you look at a 6-fold symmetry, that gives me the triangular lattice. If I try to construct something with an 8-fold symmetry, so we're 45-degree angles here, and this being lattice constant, I can directly see that this can never make something periodic. So that's why 8-fold and higher rotational symmetries are excluded. And then there was a big surprise in the 80s when then Chestman found in electron diffraction pictures with a 10-fold rotational symmetry. There's 10-fold symmetry around the central axis. And in particular, you can also see that there's very weak Bragg spots, which are very, very well defined, meaning very sharp Bragg spots, which basically means that the system must be long-range ordered. And there was a big debate about this. Linus Pauling said there is no such things as quasicrystals, there's only quasi-scientists. But in the end, the matter was settled by looking at the Penrose tiling, Roger Penrose, who got a Nobel Prize a few days ago, not for this, but for his work on black holes, but it's the same Roger Penrose. And he showed that there are long-range ordered structures that tile the whole plane, that are long-range ordered, but are not periodic. The main key insight is that you need more than one set of tiles, so more than one set of unit cells. In this case, you have these, you have the parallelograms in white and in blue, the fat one and the thin ones. And then you need a certain set of matching rules, because you could also like place them next to each other in a totally unordered way. But these matching rules mean that you will always have a long-range ordered structure. And it turns out when you analyze these structures a bit further, they have a self-similar character. So you can zoom out a little bit, take a group of tiles, replace it with a bigger tile, and the structure is reproducing itself. So you directly led to this idea of a discrete renormalization group, a discrete self-similarity, so rather similar to what we saw already in quasi-periodic systems. And in a nutshell, in the end, these systems are non-periodic, but are long-range ordered, and the story ends with then also getting the Nobel Prize in Chemistry in 2011. By now, these quasi-periodic systems, they can be created also in the lab. So you see here a dodecahedral quasicrystal grown in the lab. They also occur in nature, well, at least in meteorites. Here they have been found with a 10-fold symmetry in a meteorite, and they have been synthesized a few years ago also in bilayer graphene by simply taking 6-fold symmetric graphene, take a second layer of this, rotate the layers by 30 degrees with respect to each other and put them on top of each other. Then you will have a structure that has a 12-fold symmetry, and 12-fold symmetry of course means that the structure can also not be periodic, but you have a quasi-periodic system. So we want to do something a little bit simpler. We go down to an 8-fold rotational symmetry, and we do this by simply superimposing 4 independent 1D lattices. So this is a 1D lattice, this is another 1D lattice, there's in total 4 of them, and for the experts, they're slightly detuned in frequency just by tens of megahertz, which basically means there's no cross-interference terms between them, and you can really think of this as the sum of 4 sine waves. It's clearly not random, there's no randomness in it, it's just 4 sine waves, and it clearly cannot be periodic because 8 is a forbidden rotational symmetry. So how can we prove this, and how can we maybe see the fractal structure that comes out of this? For this, we take like a typical quantum optics approach, and we start to think about first an atom in a 1D lattice. So a 1D lattice is formed by 2 laser beams of frequency omega with momentum k and momentum minus k. And if I now take an atom in the ground state and place it in this lattice, say the atom has momentum p, then the fundamental process that happens is that it absorbs the photon from one beam and emits the photon into the other beam, and thereby changes its momentum by 2 times h bar k, so 2 times the photon momentum. And of course, after this, the process can repeat itself. So the atom can go from one momentum to the next momentum to the next momentum, and also in the opposite direction. And if you do this by just say, you take time of flight pictures after you've exposed the atoms to a quick lattice pulse, you will typically see these diffraction patterns where you see 0 momentum, plus 2 h bar k, plus 4 h bar k, minus 2, minus 4, and so on. And there's a very nice way of thinking about this. As this is a coherent process, you can also say it's actually a synthetic lattice in momentum space where a particle can now hop or tunnel from this side to that side with a coherent process, and that's then just given by the Raman weight of the 2 photon processes that I've just described here. So we can now observe this dynamics by just doing, you can either call it Kapitza-Dirac diffraction, or by illuminating the BEC with a short lattice pulse, or if you want to be fancy, you can say by observing a quantum walk on a synthetic lattice in momentum space. This idea of the synthetic lattice was actually discussed a lot and implemented first by the group of Bruce Gatway. And you can basically see here, think of a particle starting on a single lattice site. This is your BEC initially, just in one momentum class. Then you diffract it of a lattice potential for a finite time. And then you can see the different scatter orders or diffraction orders here, plus 2 h bar k, plus 4 h bar k, and so on. And you can also do this continuously as a function of time with of course, many shots. And you can really see a ballistic expansion along this synthetic 1D lattice here. So if we now do the same thing with our lattice structure after a certain time, if we take just one pair of lattice beams, so it's a 1D lattice, we see this structure here, which is basically like an ordinary simple cubic 1D lattice. With 2 beams, we see a structure here. This is a square lattice. With 3 beams, the structure becomes more complicated. And with 4 beams, the structure looks like this. And I will explain this now in a little bit more detail. And because this is very nice to see the fractal structure directly. So the way we can think about this is we can say we have now a lattice which has 4 reciprocal lattice vectors, G1, G2, G3, G4, coming from the 4 different lattice axes. If you think about this, if you think of a BEC sitting in momentum space at momentum 0, in the first diffraction, the first 2 photon exchange, it can go to one of 8 different momentum classes. Let's say it goes to the right, to the blue point here. Then it can scatter again from here, and it can go to another 8 momentum classes. It can go back to the original one or to 7 others. Let's say it goes to the upper left corner, and then from there on, it goes again to 8 different classes. Now you see that there's 2 points here, which lie along the same direction as the original points, this one and this one. And because of 8-fold rotational symmetry of the whole problem, you will get actually a full octagon of these states. And this octagon is actually self-similar to the original octagon. It's just a scaled-down version, scaled down by the silver mean. And then, of course, you can continue from this. You can say, okay, now if I take this one going from here to here as my effective 6-photon, 3-step scattering process, I can again build a smaller octagon out of this, which is in the 9th generation, and so on and so on. And I can see that diffracting around this structure is basically a quantum walk on a fractal. And how does this look in real life? Well, we start with, say, a BEC just here. We illuminate it with a very short pulse. We see the 8 first diffraction orders. If the pulse gets longer, we see here second and third order peaks. Here we see even longer peaks. And here's another nice example where we see a couple of those hexagons, of those octagons, and you can really see that they're scaled always by the silver mean. So we directly see the fractality. For the experts, we can also go one step further. We can say, let's take slightly different parameters. Here, this is now the fundamental lattice axis. So we can directly observe this fractality, and we can observe in this case up to more than a 9th diffraction order. And each of those peaks, if you want, you can label with like 4 indices, I, J, M, L, telling you how many scattering events you need in the I, J, L, and N direction to go to this. So you can really think of this as a 4D synthetic periodic lattice. And we show in this paper that you can really also get like ballistic expansion in a 4-dimensional synthetic space. But now I want to like change gears and talk about the localization transition in this potential. If we call back from what we said about the Opry tree model and what we said about that this carries through to this model, we would expect that if we start with a very weak lattice, all eigenstates will be extended. And then above a certain localization transition, the ground state will localize. And then the structure will be a bit more complicated. So excited states might need a little bit higher lattice depth to localize. To calculate where this localization in the ground state occurs, it's the easiest to start, because we are thinking of very weak lattices, to start in a momentum space picture. And there what we calculate here is the inverse participation ratio in momentum space. And basically, if you have localization in real space, you have delocalization in momentum space. So localization happens here at a lattice depth of 1.78 recoil, where we get delocalization in the spaces. And how can we show this localization, delocalization transition right away in cold atoms? And how can we do this in a way that's maybe not susceptible to the typical problem of, say, you could have slow diffusion instead of real localization, and you just have not waited long enough to see it? Well, we'll take a very different approach, and we're thinking about adiabatic transformation. We say, if I start with a plane wave, and if I now think about a periodic lattice, then if I load into the lattice adiabatically, this plane wave is directly connected to a Bloch wave, to a periodic modulation of the density with the lattice periodicity. So I can ask, what is the time tau that I need to do this transformation adiabatically from the one state into the other state? And I can test this experimentally by saying, I start with a BC, I ramp up in the time tau, I ramp back down in the time tau back into free space. I then do time of flight, as we've heard in one of the previous talks, and then I take an image. And if I did this all adiabatically, I end up back with a pure BC. If I did this too fast, I will see excitations, so atoms at other momentum classes. And just to check this was first done in Bill Phillips' group already almost 20 years ago. To check this in a 2D lattice, here you can see what is the fraction of atoms coming back to zero momentum as a function of different lattice depths and as a function of this ramp time tau. And you can basically see here, if we take ramp times above 50 microseconds, so very short times, everything is basically back to the initial state. These times are much shorter than the times that are normally used in many-body physics, because this is the situation where we can neglect the trap and where we have no interaction. So we're really just asking, how does one plane wave transform into the Bloch wave and back? And then we're almost there, because then we can say, let's do the same thing with a quasi-periodic potential. If we do this with a lattice depth of the potential that's below the localization transition, then we get something like a quasi-periodic Bloch wave. So it's not really periodic, but still the time scale to go from here to here should not be too different from what you would have in a periodic lattice, because particles only have to, on average, to move like a few lattice sites in order to find the spot where they want to be in this given density distribution. If, on the other hand, we now go above the localization transition, and we only have to go slightly above the localization transition to get a wave where the ground state is really localized to the lowest minimum, then you realize you have a very different situation. So if you now ask what is the time scale needed to reach this situation here adiabatically from this situation, you just have to think about it to realize that in the thermodynamic limit, this time scale must diverge, simply because particle density was very far out here, will all have to come to the central site here. And this density redistribution, is moving of particle or moving of quantum mechanical amplitude, if you want, will of course take time, will have a certain velocity. So in the thermodynamic limit, this time scale should diverge. And indeed, if we look at this in numerics, this is just single particle numerics, we see that, okay, the time scale diverges really as we approach something compatible with this 1.78 recoil that we saw in the initial calculation. And note the time scales here, this is now milliseconds, not microseconds. So up here, when we approach localization transition, things already get like a factor of 1,000 slower than they would be for the periodic lattice. And then we can also do the experiment. So we look at this again with a BEC of potassium-39, which we very, very clearly, very precisely tune to A equals 0. So it's as non-interacting as we can make it. And then we can again ask how much of the BEC does not come, or how much of the BEC comes back into the BEC peak as a function of this ramp time, and as a function of different lattice steps here. So you can see 3 different regimes. The first regime up here is the regime of weak lattice steps, up to 1.6 weak coil. And here, even though it takes a long time, it's approaching adiabaticity. The long time limit of this curve is going to 1. And this means that this is the extended phase. On the other hand, in this localized phase here for weaker, deeper lattices, we see something very different and something rather confusing if you want. We see A, that it takes much, much longer. B, that actually the slope is negative. So that we're really far from adiabatic. And the slower we go, the worse it gets. If we go very slow, we see almost no particles here, 20% fraction, coming back to the original BEC. So in some sense, the more time we give the particles to explore this fractal landscape, they are getting lost at the fractal, and less of them can make it back. For the experts, if we just look at the numerics, the single particle numerics, you can of course look at this also for much longer times. So this is now logarithmic time axis, and you can see that you have the typical log periodic modulations on top of this that you would expect from a system with this scale and vary. With this discrete fractal structure in it. And the red curve here is the one at 1.8 weak coil, which is the one very close to the boundary between these 2 regimes, and all of this is compatible with the signature of the localization transition happening at 1.78. Okay, let me skip this detail and just go to the last slide. This is now if you want the bridge to all of the things that are going to be discussed tomorrow. Now we ask for a lattice ramp in a deep lattice and a rather slow ramp. So the ramp where we only got 20% of the particles back on the previous slide. We ask what happens now if we have the particles weakly interacting while doing this. So now we start not with a non-interacting BEC, but in this direction going, we increase the interaction strength in the original BEC by going to a finite scattering length. And what you can see that if I start with a superfluid, so with an interacting system, you can see that we get more and more particles back into the original BEC until for a strong enough interaction, we are fully adiabatic. And our claim is that this is compatible with a shifted localization transition. So it's compatible with saying that in this regime here, the particles are still localized, but they're interacting. So this would be something like a mean field version of the Bose class. And if you look at, say, a calculation, a Kospodievsky calculation of the superfluid stiffness, you would see the localization transition happens for non-interacting particles at this 1.78. That's where the superfluid stiffness disappears. And then for some finite interaction strength, it just disappears later. So we would not say that this is a direct observation of the Bose class, but it's a strong indication that the Bose class is realized in the system. And we will look at that one in future works where we can identify that phase. Okay, the last one is just a little musing of when you think about this with the Bose class and with many-body localization, you can ask, what will be the hardest to localize? For fermions, it's pretty clear that excited states are harder to localize than ground states, because once you have extra energy in the system, this energy opens up many more scattering possibilities, and it's therefore harder to localize excited fermions. And we know of many models where the ground state is localized, but the excited states are still ergodic. For bosons, on the other hand, what we see very clearly up here, we see very clearly that superfluidity in the original system counteracts localization. It drives against localization. And in some sense, that makes sense. If I have a superfluid with a strong superfluid stiffness, because I have some interaction in the system, then it should be more robust to a weak disorder potential than non-interacting bosons should be. So for bosons, is it maybe different than for fermions that the superfluid ground state might actually be harder to localize than the high energy states? Because if I take high energy states, there should not be a difference between bosons and fermions. Quantum statistics should not play a role. I leave you with this. And as a last slide, I want to say thank you for my team. Of course, I did not do this work alone. Thank you for listening and looking forward to questions.
Okay, thank you. Thank you very much, Rick, for this fascinating talk. So it's open for questions, or let's say a few questions. Okay, are there? So please raise your hands So Li Chen, yes.
Hi, thanks for the talk. It was very fascinating. I'm sort of more of a mathematician, so I don't completely get the physical picture. But when you mentioned this localization time scale, where you kind of go from your plane wave to this, you know, a little spike in your sort of quasi block, and you mentioned there's this adiabatic. I just kind of want to know, like, what does that mean? So my understanding is that you have your Hamiltonian and you slowly crank up your quasi-periodic potential. Is that what I'm understanding?
Yes, it's exactly what I mean. Just let me go to the slide. That is exactly how you should think about this. Let me maybe start with the periodic part here. So basically what we're doing is we're saying, if I have an Hamiltonian where the eigenstates are plane waves, so that's the Hamiltonian with lattice step 0, and then I can slowly increase the lattice step, then we would argue that, of course, you will follow. If you think of you're initially in the ground state, then you will adiabatically follow the ground state if you change the Hamiltonian slow enough. And then you also end up in the ground state of the new Hamiltonian. So if you adiabatically slowly increase the lattice depth, everything that was in the p equals 0 momentum wave will go into, for non-attacking particles, the q equals 0 quasi-momentum 0 Bloch wave. And basically what we're doing here is we're saying, well, if I change the Hamiltonian adiabatically, and then also change it back adiabatically, and I was in the ground state initially, I will also end up purely in the ground state. Which basically means, because we start with a pure BEC, and I should maybe have mentioned that we started with a pure BEC here, we also end up with a pure BEC, with everything being in a BEC, so you get a picture like you have here. If, on the other hand, you go quick, you ramp up quickly and ramp down quickly, then you will create diabatic excitations. You will not end up fully in the ground state, and you can see this here by seeing these excitations around this. So it's really, in some sense, we can measure the fidelity of the state transfer from one state to the other and back.
Oh, I see. Okay, thanks.
Thomas, yes.
Yes, I'm curious. Yeah, exactly on this side. Here, it seems like in these quasi-periodic systems, usually the localized state are very localized on a very on few sites, and so like this when you try to be adiabatic, it's like very different systems. So I wonder, what very different states, like from the completely delocalized one to the localized one, which is localized on a very short distance. Mm-hmm. I wonder where you tested this method, like this fidelity method, somehow on a true disordered. You did some numerics here on the quasi-periodic. Have you tried with a truly disordered system and see whether it looks slightly different?
Well, let me maybe go back to the 1D case. I think that's where you can see this already. This is the slide I want. So if you think of, this is now in tight binding simply, but what you see here is the localization length for a typical Anderson model. I believe it's box disorder. I have to check. So you see the localization length diverges, of course, at 0, because at 0 you are delocalized, and then for any finite disorder strip you're localized. And you can see that in some sense it comes down relatively smoothly. While the open tree case here only localizes at this point, but then it comes down very, very quickly. So indeed, when I saw these graphs that we just saw before, where it's just really localized to like the one central minimum, I was saying, well, telling the student, you're basically far too high above the localization transition. Let's make it closer to the localization transition, just say 10% above it, so that we really see a wave function that's still expanded over many lattice sites. And the student came back to me with calculations, and it really shows that you have to be just epsilon above the localization transition, and then you get like a finite localization. If you, as soon as you're a few percent above the localization transition, it really comes together to the lowest minimum only. So it's a very, very sharp transition in that sense. And it also, of course, tells us that it's, even in finite sized systems, will be very hard to cross through adiabatically.
Thanks.
I hope that answers your question.
Okay, Thierry.
So Uli, first, thanks for the very nice talk. Second, a question which I'm not sure I can quantize fully, but in 1D, as you show in the slide you're showing right now, actually far from the threshold, which is different for quasi-periodic and disorder, let's say there is very little difference between quasi-periodic and disorder, which was, of course, used positively to study this phenomena. Is it the same in 2D? Or did you see more marked difference from the fact that it's not really a disordered system? Or at the end of the day, is it about, again, the same if you have a quasi-periodic than if you were putting true disorder? Or is it more marked? And I don't know how to quantize more marked. So
I think I can not quantize it, but I can mark it in two ways. I can, for instance, say if I take the 2D open tree model, and you look at the plot we have here of the
yes.
participation ratios
Yes.
as a function of energy and as a function of disorder strength, you can really see here, right? In real Anderson, you would say that in 2D also all states are localized. What you see here is that some states exactly in the middle of the spectrum are not necessarily fully localized.
Yeah, but if you go to stronger disorder, in a way, okay, yes, in 1D, in 1D, it's a more an abrupt transition. I agree. Okay.
If you go to this situation here, if you go to like this analysis we did here, which, well, analysis is a big word for that. Whatever the prefactor is, there will always be combinations of beta times n that the cosine is close enough to 0 that this 1D system will not necessarily be localized. So it's a funnel that gets less and less and less, but a few of those states will persist to very high energies.
So you say it's not a little bit like in 1D where when you pass the threshold, in a way, everything is localized again and you don't make difference. Here you say there is more coexistence of localized and delocalized state.
Here I would actually, to be honest, I don't even know my own conclusions here.
Okay.
On the one hand, it is as you said, we have these very few states here which remain delocalized for very long times, for very strong things. I call them pseudo-extended because in some sense they locally scale like a 1D state, not like a 2D extended state. But if you look at big enough scales, it's a network, so it's extended. On the other hand, I would claim that it's maybe even more disordered than a real random disordered state would be because you will not have local ergodic bubbles. So in that respect, for MBL, I'm kind of hoping that this system is better for studying MBL than the real disorder cases. But it's an open question. I mean, this is now mostly based on intuition.
Okay, thanks.
Okay, we're going to take two last questions and then we'll have a quick word by our web expert for how to work in Gatherton. So now I give the question for Nicolas Laflorency.
Yes, hello. Yeah, so I have a simple question. I was a bit confused by, at the end of your talk, you said, if I understood correctly, that bosons in 2 dimensions should be easier to localize at high energy as compared to ground state. Is it something you said?
That is what I said, and it's not 100% true, not necessarily true. It's something we should discuss. So let me go back to this. So in fermions, it's pretty clear that the excited state is going to be harder to localize than the ground state because of the excess energy you have in the system.
Yeah,
that's pretty obvious. Now, if I'm at this high energies, bosons at this high energy should be as hard or easy to localize as fermions at this high energy, because I'm far away from degeneracy, so it's all classical particles in a sense, so I shouldn't see a difference between bosons and fermions.
Mm-hmm.
And now I can ask what happens if I go down with bosons. And what we saw here is we see that the interaction term, the mean field term, we see that the mean field term in bosons strongly wants us to be superfluid. So that term counteracts localization. So in some sense, I take away the excitation energy, but I get this new superfluid order, which is kind of robust. So the question now is, which one of the two wins? Will it get harder for bosons to localize at cold temperatures or not? If I think about superfluidity. And again, I don't know the answer. I'm just thinking that this is a very interesting question to ask.
Yeah, but I think it really depends on the interaction between the particles, right?
Of course, it will, yes, sure. If you have non-interacting particles, then they will probably be even easier to localize than non-interacting fermions because they will only occupy the single particle ground state.
Yeah.
Yes.
Okay, thank you.
Okay, Shiwen, last question.
Okay, so thank you for the talk. I have a quick question for the 2D Andrew Aubrey model. Can you go back to the previous slide on the cosine?
That was probably this one.
Yeah, this is the previous. Yeah. The one, yeah, the next one probably.
Okay. Yep.
If I understand correctly, so this one has the delocalized state or tangent state because for the M and N direction, the two frequencies are the same actually where you are picking.
Yes.
I mean, both beta beta.
Yes.
So
Yeah.
it's exactly the strong resonance case. I think mathematically there are existing results saying like in the M and N direction, if you pick like beta 1, beta 2 to be strongly irreducible, then you have localization for large disorder, right?
You're totally right. I mean, I can take other realizations of a 2D open tree model that will not show this state to the same degree. The trick is that if you just like go to beta 1, beta 2, which are different, then you have to be careful that you don't lose OP duality. But one thing that you can do is you can say, I take this 45-45 axis, let's skew them like this, the angle between them gets bigger or smaller. And that way I kind of lose the symmetry that I have here. And thereby you can like reduce the amount of those states. You will always have lines, because you just take the sum of two cosines, you will always have lines that have almost no disorder. But if these lines are not aligned to the lattice axis, but say, okay, I have to like jump 10 in here and 1 in there to get to the next state that's resonant, and then 10, 1 again, then these lines will have very, 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 very weak tunneling. So these lines, because it's a high order process, so you can like take situations where these pseudo extended states will not be important at all. And I'm even not sure whether they will be important at all if I think about a many-body localized system in this kind of configuration.
Okay, yeah, thanks.